In this presentation, we will talk about two-level battery charger using a two-level CDC converter. Also, we want to discuss the analysis regarding to the power and control stage. And finally, to end with this lecture about the modeling and simulation of this converter. Okay. First of all, here we have the topology with what we will discuss. And as you can see, this battery charger is configured using a two-level DC converter, typical two-level DC converter, which load is a battery. As you can see, this two-level DC converter is configured using two switches, level as Q1 and Q2. And also, as you can see, all the storage elements, I mean, the inductor and capacitor, are we are including their strike residues, to put it this way. Basically, the strike resistor regarding to the inductor and the strike resistor regarding to the capacitor. Also, you can see the battery is modeled using a series resistance with that I label as a RB and a OB voltage, which is the internal voltage of this battery. Also, each switch is configured or implemented using a MOSFET device. The input voltage is the UVD, and I assume that this input voltage basically using a DC voltage, including an AC ripple component, basically. Of course, in order to know what is the operation of this converter, it's mandatory to know what is the switching structure. As you can see in this plot, I graph the switching strategy, which I divided by two parts, basically. The part one, I mean, the time range between 0 until the time TS, Q1 and Q2 are operate in order that Q1 is closed and Q2 is open. Now, when the time goes from the D time TS until TS, the switch Q1 is open and switch Q2 is closed. So regarding this, taking account this information, we can define the switching function. This switching function, as you can see here, I call it as a function of T, and the definition is here is a piece-like wire structure. I mean, this switching function take the value 1 when the time goes from 0 to the time TS, and take the value 0 in another semi-cycle period of this switching cycle. I mean, D time TS until TS. Of course, TS is the period switching of the system. Okay, now we are available to make the analysis of this system. Okay, what is the topology when the time goes to, sorry, here, let me fix this. Okay. Okay, so what's the topology of this system when the times range goes to from 0 until D time TS? Is this topology here? Of course, the Q1, when it's conducting, we put a resistance between drain and source of this MOSFET, which which tell us that there is some loss of conduction of this device. So the goal in this topology is basically get the equation relating to the voltage of the inductor and the current of the capacitor, and also the current, the battery current, basically. So applying the KVL and KVC, basically you can get the equation related to this topology. Now, if we apply the small ripple approximation principle, these equations can be can be in this way, basically. Of course, we assume that the ripple component is less than the DC component, which is the normal condition in the real life, basically. Okay. Now, what is the topology when we are located in the second switching period, basically? Okay. Here we have another topology. Let me tell you something before to go the next. I call it as well RIN, and RIN is the combination of RDS plus RL. Okay, it's the combination about the summation. Basically, it's the summation of RDS and RL. Okay, perfect. So as in the early procedure regarding to the first topology, we can derive the equation related to this topology, applying the same techniques. I mean, KVLs and KVCs, basically. When we do that, we can get these equations. These equations related to of course, the inductor voltage and the capacitor current, and of course the battery current as well. And applying to the small ripple approximation, we can finally get the equations relating to this topology. So now we already calculate the equation related to the topology 1 and topology 2, So now we can get, or we can apply the inductor voltage second balance and the capacitor charge balance. Regarding to the first one, you know that in a steady state condition, this the average inductor voltage is equal to 0. Only, of course, when the converter operates in a steady state condition. So if we can get the equations regarding to the first topology and the second topology, we can get this equation, basically. And applying the capacitor charge balance in the same way, you know that the current through the capacitor over a switch period is equal to 0. Of course, we assume that this converter operates in a steady state in the first time. So here we have both equations that we can use in order to calculate the relation between UBC and IL, because our unknown variables are UBC and IL, and our known variables are D and UBOB, basically. Finally, if we can solve this equation system, we can get the finally variables IL and IBC, and as you can see here, when you have the structure of this equation. Okay. So with this information, now we are able to calculate the capacitor and inductor in order regarding to the ripple max percentage that the problem. I mean, in this problem, it's supposed that the problem give us the max ripple available for the current, inductor current, and the capacitor. So first, in order to calculate the inductor value, it's easy to draw what is the curve about the inductor current over switch period. As you can see here, we can calculate, for example, the scope of this segment between this point and this point. I mean, IL0 and IL max. And as you can see from equation, basically from this equation regarding to the first topology, and as you know, UPL is the derivative of IL divided by, multiplied by R. We can note that this structure belongs to a scope of this segment. So we can take this equation and put it here. And here we have our first scope. But also, if you can see this figure, we can also get the same scope if we by simple induction. I mean, you know that regarding this figure, you know that the scope is basically 2 times delta L divided by TS. So both equations must be equal, you know. We need to force to equal because we're talking about the same scope. In order to do that, from this expression of this balance, we can solve for L. And this equation finally return us the value of the inductor regarding to the filter phase. Okay, so we already done. I mean, we already calculate the inductor of this system so far now. Now is the turn of the capacitor calculation. And we proceeded in the same way as the inductor calculation. We can take out the scope regarding to the first equation here. This one is the first scope divided by C, you know, because I see nothing more than, it's nothing but the voltage through the capacitor divided by the derivative of the voltage through the capacitor divided by C. So if we can take this equation here and put it here, basically we can get the first equation related to the scope. And the second information that we got from this figure is the scope basically. And as you can see, the scope is the negative sign, of course, because it's a decrease in the by. Now we can get the second expression for the scope. So how this is, since this scope are the same, so we can get we can force this equation in order to equate equation. And from this equation, we can solve it by UBC, by C basically. Now, and if you do that and solve for C, now we can get finally expression in order to calculate C. So with this equation, we can calculate the L and C for this converter. It's important that you know that this converter includes trace resistance. So it's not an ideal converter. Instead of, for example, we can try to do the same with an ideal converter, which not take the values of not taking count this storage resistance. This is you should keep in mind because this algebraic manipulation could be more hard for in compares with a comparator in an ideal comparator. Okay, let's continue. So from these equations, or basically from equation regarding to the first topology here and the second topology here, we can derive the dynamic equation in its switching model way. Basically, if you can see instance of using a D, here we have an ST the switching function. So how you can see, since you can find the switching function in this equation, we are talking about a switching model. Okay, so these three equations finally represent the switching model of the system. Now, if we use the average operator, which is present in this in the equation regarding to the this expression, we can get finally the average model by replacing basically the switching function by d. D is in a constant value, you know, and replacing the instant values by its average value, as you can see between these parentheses, no curve parentheses, within a sub-index labeled as TS, which means that this value is in a period, is an average value over one switch period. And as you can see, this basically the same equation, but replacing st by d, and replacing the instantaneous values of the variables by each average option in order to put in this way. Okay, now here we have the switching model here and the average model. Finally, if we can take this average model and apply it to Taylor series, and then we can, and taking account the small signal values in order to get the linear model, we can finally get a small signal model of the comparator, including the battery charge. And once you apply this, you can get finally this equation system, which is represent a small signal model of the comparator. So now we are able, for example, to convert this space. This is in a way of state space way. If you can see here, we have the state equation, and here we have the output equation. So taking this information, you now are available to convert this system in Laplace domain and finally get the transfer function of the system. Or, for example, you can take these equations of the system and apply in a state space domain, and apply, for example, a quadratic regulator in order to get a controller for regulation the system. Okay, but as you know, we now we need to, I mean, since you have a linear model, and at the same time you can calculate, and you can modulate modeling basically and control it, but it's necessary to design a modulator as well. But in this case, since we deal within a DC-DC converter, it's proper to design a modulator using, for example, a PWM modulation. And this PWM modulation we can derive using, for example, a sub-fit wave, as you can see here, and the duty ratio, as you can see here, coming from a controller. And applying this definition here, we can get finally the switching function, which represent basically the state that we take each switch involved in this comparator. Okay. So far now, we are get finally all the equations and analysis regarding to this comparator. So now it's necessary to know what is the control system of this comparator. And as you can see here, we can basically here you can see what is the strategy of the control. And basically we will use an PI controller the modulator, which design is presented in this slide. And finally, this modulator will feed, we will feed this modulator. We will feed within a switching function to this switching model, which is the real model of the converter. Okay. And with this information, we are able to implement a simulation in MATLAB, for example, in this case, using Simulink of MATLAB, in order to know what is the behavior of the system whenever you know these the input variable of the system and the output variable of the system. And the model implementation that we use in order to simulate the system is depicted in these slides you can see here. And for sure, you can see in this slide basically the behavior of the system in face of some, for example, in this case, of one step change in the reference value. For example, here in this figure, you can see the reference value of the battery charger against the battery charger measure value. And as you can see, the behavior of the system is practically close to the single order or the first order system, and almost with no overshoot and practically neglected steady state error. And of course, when the time reach 60 milliseconds, there is some step change in the battery charger reference, and the system behavior response with this cure close to the first order system as well. Here you can see also the cure of the dynamic response of the inductor current, and as you can see, follow the same wave shape of the battery charger, because the system almost reached the steady state. In the steady state, the inductors basically is close to a short circuit, and the capacitor is close to an open circuit. So basically, the inductor current is very similar to the battery charger. So take basically the same value and the same wave format. And also you can see here the capacitor voltage, which is basically dynamic response. I mean, the behavior of the capacitor voltage is proper with the dynamic response. And you can see here the duty ratio of the system, which responds very well as in the other variables. So you can see here a good response. Okay. So this is the presentation, and here we have basically the model of the system, the simulation. Thank you for your attention, and see you in the next presentation.